All right, everybody, so we are starting chapter 13. Again, pull the PowerPoint from D2L or the shared class files. The beginning of this chapter, so this is a chapter where we are revisiting solutions. It is in your best interest if you look back at solution material from chapter 4 and 1211, molarity calculations, dilution calculations, which remember that's M1V1 equals M2V2. Just general properties of solutions and all that kind of stuff. You need to know chapter 4 really well. This chapter just jumps right on top and adds a bunch more information. So go back and look at that. Okay. Now the beginning of the PowerPoint goes through some basic information. What's the solvent? What's the solute? All that kind of stuff. You need to read that stuff and know it. Again, a lot of it's in chapter 4. A solution is a homogeneous mixture. It can't be separated by filtration because if the solute is dissolved, it'll pass through filter paper with the solvent. You can't evaporate the solvent off and recover your solute. Blah, blah, blah. This is stuff that you should already know for the most part. There are a lot of different types of solutions that you can make. You can dissolve solids in liquids, gases in liquids. You can mix gases together. Keep in mind there can only be one solvent. Whatever substance there's more of than anything else, that's the solvent. You can have many solutes. So if I'm talking about a can of Coca-Cola, I would say that the solutes in a can, actually the solvent of a Coke is water, but the solutes, there are many of them. All the ingredients on the label, you have sugar dissolved in the water, you have carbon dioxide, you have all kinds of different flavorings and sweeteners. Phosphoric acid is in there as a preservative. So lots of different things. When you look at metals, alloys are actually solutions where you've mixed different metals together. But again, the one that is the primary constituent of an alloy is the solvent. Specifically, if you have a metal alloy with mercury in it, it's called an amalgam. It's just a common term that comes up every now and then. But let's see. So when we form a solution, just to tie in what we did in chapter 11, we introduced intermolecular forces. Well, essentially, there are intermolecular forces between the particles of the solute. There are intermolecular forces between the particles of the solvent. And if we want to form a solution, then the only way that's going to happen is if the new attractions that we form between the solute and the solvent, if those attractions are strong enough and if they're beneficial enough to help stabilize the molecules or ions, then that's when the solution is going to form. Okay? And that process of a solute being dissolved by the solvent, the process is called solvation, which is just a general term. If your solvent happens to be water, there's a more specific word. Instead of solvation, we could call it hydration. Anytime something has water added, you are hydrating it. All right, so how does solution occur? Well, essentially, let's just say we have a crystal of sodium chloride. The water molecules come in, and they pull apart one particle at a time. In an ionic compound, each particle is an ion. So I have the chloride ion or the green spheres, so that's a Cl-. If you notice, the way the water molecules interact with the Cl- is actually specific, where all these water molecules, the hydrogen atoms are turned towards the chlorine because the partial positive on the hydrogens are attracted to the negative on the chlorine. Again, from chapter 11, this is what we call the ion-dipole interaction, or the ion-dipole attraction that can occur. If we look at the sodium ion, again, both of these are pulled out from the NaCl. The sodium ion is also surrounded by water, but now all the water molecules are turned the other way so that the negative on the oxygen is attracted to the positive of the sodium ion. All right? So there are some specific details that you need to notice about how compounds dissolve. So, solutions are formed when the intermolecular forces of the solute and solvent particles are similar to each other, and the attractions that are formed are strong. When does that happen? Well, typically it's when we have similar molecules. We learned in 1211 the phrase like dissolves like. Polar compounds, which have dipole-dipole forces, typically dissolve well with other polar compounds because the dipoles of the solute particles and the dipoles of the solvent particles can interact in advantageous ways. Ionic compounds also dissolve because, again, you get the attraction of charges. And then if you have nonpolar compounds that don't have very much charge to them at all, because London forces are very weak, they will mix with other nonpolar compounds. But if we try to mix polar compounds and nonpolar compounds, that's when they usually separate. Everybody's heard the term that oil and water don't mix. It's based on intermolecular forces. So again, two nonpolar molecules are going to interact well. Two polar molecules will interact well with the partial negative of one, interact with the partial positive of the other. Hydrogen bonding is an extreme version of dipole-dipole. So of course, polar compounds, hydrogen bonding, and then often ionic compounds will all dissolve well with each other. So if I have a given solute, carbon tetrachloride, that's my solute, and I want to dissolve it into a solvent. Question is, would I be more successful dissolving carbon tetrachloride into water, or would I be more successful dissolving carbon tetrachloride into hexane? Which solvent would it be more soluble? I have to understand the properties of carbon tetrachloride. If you draw out its Lewis dot structure, which again, take a second and do that, we need to decide if it is a polar or nonpolar compound. After that, then we need to look at our solvents and decide whether they are polar or nonpolar, and then we're going to pair up the ones that are more similar. Okay, so if you've checked that, you should have that carbon tetrachloride is a nonpolar compound, water is a polar solvent, hexane is a nonpolar solvent. Remember again, hexane is a hydrocarbon. Hydrocarbons are always nonpolar unless you introduce an electronegative element into their structure. So, carbon tetrachloride should be more soluble in hexane than it is in water. Next one, same process. If you draw out the structure, this time urea, again, go ahead and do it. But urea is a extremely polar molecule. It actually has hydrogen bonding, so it's going to dissolve really well in water, not very well at all in carbon tetrachloride, because again, water is polar. Carbon tetrachloride, this time carbon tetrachloride is a solvent, and it is nonpolar still, so polar compound won't dissolve. All right, iodine. So iodine, and this would be the iodine molecule, I2, that's the normal way that iodine exists, is a nonpolar compound. So of these two solvents, it's going to dissolve better into benzene. However, iodine actually will dissolve in water decently. Not quite as well, but still, you can dissolve a reasonable amount of iodine in water. Again, think about for a second why that might be. Why would iodine, which is a nonpolar compound, still dissolve pretty well in water compared to other nonpolar compounds? Okay? The answer to that is iodine is a really big molecule. It's only 2 iodine atoms, but iodine is pretty far down on the periodic table. The atoms are large, so the electron cloud around the iodine atoms is very large. And we said in chapter 11 that the larger the electron cloud is, the more polarizable the electrons are. Okay? And if it's polarizable, that means that we can shift the electrons to one side, create a partial negative, and leave a partial positive on the backside. So if iodine can easily be shifted, then if a water molecule comes up to it, if the oxygen approaches the iodine, it's going to push the electrons away and create a partial positive that can create an interaction. Okay? So because it's so big, it's more polarizable. That's going to allow it to dissolve in a polar solvent better than a small molecule would. All right, last one of these, methyl alcohol or methanol. It should certainly be more soluble in water because OH have hydrogen bonding. So hydrogen bonding in water, they're going to interact well. Now, when we dissolve, there are different ways that compounds can behave when you dissolve them in water. Okay? Covalent compounds, when we dissolve them in water, they tend to stay, the molecule stays intact. So if I have a crystal of glucose, it is a polar molecule, so that's why each purple oval, it should be a partial positive and a partial negative in the picture. It just doesn't have the partial symbols. But each molecule, when the solvent comes in and takes it away, the molecule stays intact. It doesn't break into pieces. Okay? So it goes from being solid glucose in the crystal to, once it's surrounded by water, then it's going to be aqueous. If we wanted to write that in the form of a chemical reaction, even though it's technically a physical change, this is how it's normally written at the bottom, where solid glucose, when I add water, again, the water is not really a reactant here, it's just allowing a change of physical state to occur. We're going from solid to aqueous. And so something is either a solvent that's needed for the process to occur. Sometimes if you have a catalyst or something like that, where it's not really a reactant or a product, we often put these things on top of the arrow. So even if I didn't put the water there, to go from solid to aqueous, it should be obvious that there was water added. So it's kind of just a shorthand that you need to notice. So then if I go to sodium chloride, again, when I add sodium chloride in water, it kind of feels like it should be written like that. Students always want to put water as a reactant when we say we added water, but it's not a reaction, so that's not really how we want to write it, because in that reaction, it's not balanced because the water just disappears. So a better way to write it, again, is either with or without the water on top of the arrow, but I'm definitely going to show the physical state. NaCl solid is going to turn into NaCl aqueous, but by now we should all know that ionic compounds that are aqueous are actually split apart in the ions. So I get sodium ions aqueous and chloride ions aqueous. So again, recognize that shorthand. We will write a lot of reactions that way for the rest of the semester. Now, the interaction is occurring, again, we mentioned already, it's the ion dipole forces. The water molecules surround the sodium. Sometimes with some metals, the interactions between the water molecules and the metal can be pretty long lasting. And sometimes there's a very specific number of water molecules that tend to attach. When they attach, that's what we call metal ligation, Ligation. But each metal can interact with a different number of molecules. Sodium interacts with 6. I think copper interacts with 4, if I remember right. I think nickel interacts with 6. So every metal has a different, again, it's the coordination number. It's the number of atoms that are attached to the one that we're looking at. Chloride apparently specifically attaches to 4 water molecules. So that's not something you need to memorize. But again, when we start writing reactions in the qualitative analysis labs, you're going to have to write the true form that some of these metals exist in. And sometimes they're going to have water molecules attached, or it may even be ammonia molecules that you see. So you'll observe that in lab, but essentially, like again, copper ammonia complex is going to come up later. That's going to be a copper atom in the middle with a +2 charge, and then it's going to have 4 ammonia molecules that are kind of attached to it through these interactions that we have. So, based on these interactions that we have, and we've said a couple things about it, are ionic compounds soluble in water? So think about that for a second. The answer is sometimes they are. Some ionic compounds are soluble in water. Some ionic compounds aren't soluble in water. The way we know for sure is that in 1211, we memorized the solubility rules. We know that most compounds that have chloride are soluble. The exceptions to that are silver chloride, lead chloride, and mercury chloride. Okay, so those are insoluble, but everything else with chloride is soluble. Why is that? Why are some ionic compounds soluble while others aren't? The answer is it's based on these ion dipole forces, because as I said before, we have to break apart the solute particles, so we have to break those interactions. We have to break apart the solvent particles, so that's another force that we have to deal with. And then when we bring the solute and the solvent back together, we're forming a new interaction. So the question is that advantageous or is it not? These are some considerations that we have to think about. Again, that's going to come up in a little bit in the slides. So that's a good place to cut off for now. We will deal with deciding which compounds will dissolve and which ones won't in the next video.